Hi everyone. This lesson will talk about one of the fundamental tools that modern cryptography is hard to imagine without, the hash functions. Your devices use them every day. Hashes underpin secure web connections, password storage, and many other things often taken for granted. This lesson will cover the main features of hash functions, their objective, applications, and compare them to ciphers. Fundamentally, hash functions take an arbitrarily long but finite input and produce a fixed-sized output based on that input. The result of applying a hash functions to the input data is called a digest, or a hash value, hash code, or checksum, or simply a hash. This digest serves as a reproducible representation of the input that detects any accidental or intentional change. Importantly, a digest is also very compact, usually much smaller than the original data. There are several distinctive features about cryptographic hash functions that make them an indispensable tool of cryptography. First of all, they're efficient to compute for any finite input. The same input to the same hash function will always produce the same output. They are also hard to trick. A slight change in the input results in a drastically different output. And it's hard to guess or work back to an input that will produce a given output. The algorithms of particular hash functions may vary greatly from one to another, but the required and desirable properties they should possess to be of use in cryptography are well established. Hash functions are commonly used for data integrity, to verify the data received is indeed the data that was sent, with no alterations, or that copies of data stored in different locations are in fact the same. For example, Alice has to send her fellow scientist Bob a novel formula the lab developed, so she attaches a file to an email and provides its digest. When Bob downloads the attachment, he calculates the hash as well. Bob sees that it does not match the number Alice provided and becomes alert. Maybe there is nothing to worry about and Alice just sent an older file by mistake, or maybe some malicious party intercepted the message. In any case, Bob can let Alice know and request the correct file. This check has saved him from misunderstanding and potentially more serious consequences. In a similar scenario, using the hash value of the molecular plot to create a digital signature would save Alice and Bob both space and time, compared to splitting the data into smaller blocks, sending each of them directly, and composing back together. In practice, digital signature algorithms usually do the hashing for them automatically under the hood. Like here, Wolfram language by default uses SHA-256 hash function. Hash functions are used ubiquitously for achieving data integrity objective. For instance, software publishers often include the checksum along with the program files for the user to be sure they're about to install the right thing, not a corrupted file, or worse, a virus. It is also important to note that although hashing of an input produces an output that is visually indistinguishable from encryption, these two cryptographic instruments should not be confused. Probably the first difference that comes to mind is that encryption and decryption require a key, while hashing does not. Well, that is often true, but not always. While most of the widely used hash functions are keyless, this fact is not a definitive feature. For example, message authentication codes are keyed hash functions. Moreover, a keyed hash can be created from a cipher by taking the last n bytes of data encrypted in some way. By design, encryption is a two-way transformation, there and back again. And hashing is a one-way operation, then even using a key does not revert it. That is the main difference. Another fundamental difference lies in the objectives of two primitives. Encryption tries to provide confidentiality, keep the data content secret from anyone but the possessors of the correct decryption key. When an encrypted message is sent, the receiver should already have the key to decrypt it from a previous key exchange or agreement with the sender. Hashing aims to first of all provide data integrity. Make sure the data was not modified or manipulated. The hash value is usually sent alongside the original message, so anyone can verify at a later point in time that the current hash of the message matches the claimed one. Keyed hash functions can provide both data origin authentication and data integrity objectives, but not confidentiality. In the next lessons, you will learn how the security features of hash functions make them so useful in cryptography.